Okay, so we're going to do the final part of normal distribution, which is looking at hypothesis testing. So in terms of the actual hypothesis testing itself, it's the same type of format in terms of a null hypothesis and alternate hypothesis as binomial, but the way we look at hypothesis test is different. So we are always looking to see whether our assumed mu, sorry, my TV starting, we're always looking at whether our mu is accurate, okay? And what we assume is that if we have a variable x which is normally distributed with a mean of mu and a standard deviation of sigma, then if we were to take the means of lots and lots and lots of different samples, we would assume the means to be normally distributed with a mean of mu still, excuse me, and a variance of sigma squared over n. So remember that actually what we write here, sigma squared, is the variance. So this section here is the variance. It's just that it's almost always written in the format of something squared. Here, because whatever this answer is quite often a really horrible number, we're writing it as the variance. It's really important you remember that because it will completely impact and change your answers. So the easiest way to do this is just go straight into an example. So what I'm going to do is I'm going to leave those formulae there so that they are there for the first example. So we're on the last 3 slides of the normal distribution PowerPoint. So a certain company sells fruit juices in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3. The company claims that the mean amount of juice per carton is 60 millilitres. A trading inspector has received complaints that the company is overstating the mean amount of juice per carton, and he wishes to investigate this complaint. The trading inspector takes a random sample of 16 cartons and finds the mean amount of juice per carton is 59.1. Using a 5% level of significance and stating your hypotheses clearly, test whether or not there is evidence to uphold this complaint. So, we need a null hypothesis, which is that our mu is 60. And the alternate, well, it says the trading inspector is investigating that the company are overstating. So that would mean that mu would be less than 60. So I need to assess the means. So the means should all be normally distributed with a mean of 60 and a variance of 3 squared over 16. So therefore our standard deviation is the square root of 3 squared over 16. So we need to remember that for our calculator. So what we are testing is the likelihood of getting a mean that is less than or equal to 59.1. And we want to compare this to the 5% significance level. So I'm going to look at, if all the means are normally distributed in this way, I'm going to look what the likelihood is of getting a mean of 59.1 or less. So I'm going to go to the distribution in my calculator. I'm going to go to inverse normal. Sorry, no, I'm not. I'm going to go to normal CD. Sorry, it's because I've just been doing an example using the inverse normal. So I'm going to go to normal CD. Because I want less than 59.1, my lower bound is as small a number as I can think of. My upper bound is 59.1. My standard deviation is the square root of 3 squared over 16. And my mu is 60. So the likelihood of getting 59.1 or less is 0.115 to 3 significant figures. So 0.115 is greater than 0.05. So that means there's a more than 5% chance of getting a sample size of 59.1, assuming the mean is 60. This means that we accept our null hypothesis because there's no evidence to say that we should change it. There's no evidence to say it's different. So there is no evidence to uphold the complaint. Because the complaint was that it was less than 60, but from the sample taken, it is within the acceptable probability that we could get a sample size of 59.1 as the mean. So this is greater than 5%, it's actually an 11.5% chance. So therefore we would consider it likely enough to accept the null hypothesis. There's no evidence that our mean has changed. I've taken the second example from the exercise because we have only seen one where we're accepting the null hypothesis. So I have deliberately chosen one where we're going to reject it. But let's just look at how we'd approach the question. So the times taken for a capful of stain remover to remove a standard chocolate stain from a baby's bib are normally distributed with a mean of 185 seconds and a standard deviation of 15 seconds. The manufacturers of the stain remover claim to have developed a new formula which will shorten the time taken to be removed. A random sample of 25 capfuls of the new formula are taken, and the mean time for this sample is 179. Test at the 5% significance level whether or not there is evidence that the new formula is an improvement. So our null hypothesis is that the mean is 185. That's what we're assuming to be true. And our alternate is that the time taken has improved, so the mean is less than 185. So if we're assuming 185 is true, then the means should be normally distributed with a mean of 185 and a standard deviation, a variance of 15 squared over 25. So therefore our standard deviation is the square root of 15 squared over 25. So I want to know what the probability is of getting a time of 179 or less, because that is really our cutoff. What is the probability of getting 179 or less given that the means should be normally distributed in this way? What I didn't do last time is I didn't sketch, which is what I always encourage you to do. So this is the means of the normal distribution. So we want to know what the probability is of getting a mean of 179 or less, because if it's a big enough probability based on this mean, based on this normal distribution, then we can say the formula hasn't been improved, but we want to check that probability first. So our lower bound is still going to be as small a probability as we can get, so normal CD minus 1 times 10 to the power of 99. My upper bound is 179. My standard deviation is the square root of 15 squared over 25. And our mean is 185. So the probability of getting a time of 179 seconds or less is 0.0228 to 3 significant figures. So that probability is smaller than 0.05. So there is a less than 5% chance of getting a time of 179. Because of that, we reject our null hypothesis and accept our alternate hypothesis because there is sufficient evidence that the formula has improved. Because a time of 179 seconds is so unlikely if our mean is still 185. It's so unlikely to get this time that our mean must be wrong. We must have improved that mean, and the mean must now be smaller, because this happening in our sample is so unlikely that we can reject the mean of 185, which is our null hypothesis, and accept the alternate that it is less than that. Okay, so we're going to have a look at a two-tailed. The two-tailed that we're going to look at is also introducing critical regions. Now, in the book, it goes on and on about the fact that with a critical region, you should standardise it and do this really quite complicated formula with standardising it and using the percentage points table. Do not do that. It also then says you could use the inverse normal distribution on your calculator. There is never going to be an example or a situation where you would need to standardise it. So don't do it. Just use inverse normal. Excuse me. So you're just going to do it based on what I'm going to show you here. Do not do it based on the way the book does it. So, final example for normal distribution. A machine produces bolts of diameter D, where D is normally distributed with a mean of 0.580 and a standard deviation of 0.015. A machine is serviced, and after the service, a random sample of 50 bolts from the next production run is taken to see if the mean diameter of the bolts has changed from 0.580. The distribution of diameters of bolts after the service is still normal with a standard deviation of 0.015. So the fact that it has the word changed tells you it's two-tiered, okay? So that's what we're looking at, is we're looking at a two-tiered. Find at the 1% level the critical region for the test, stating your hypotheses clearly. So my null hypothesis is that the mean is still 0.580, and my alternate hypothesis is that it isn't still 0.580. We're testing whether the machine's gone wrong and the mean bolt has changed. So if it's still the same, my means, that should be mean of D, should be normally distributed with a mean of 0.580 and with a variance of 0.015 squared over 50. So therefore our standard deviation is the square root. I always do this so I don't forget to type this into my calculator rather than that. So I want to find the critical region. So I know that if I'm modelling D bar, so the means of all my samples, the mean should be 0.580. And I want to find the critical region, so the cut-off points at either end, that would have a less than 1% chance of occurring. Now, like with binomial, if I've got a two-tier, that 1% is split across both ends. So getting more or wider than this diameter has to be 0.005, and getting less than this diameter is 0.005. So the probability that my mean diameter is less than or equal to D1, doesn't matter if it's less than or equal to, is 0.005. So now I'm going to use inverse normal. So my area is 0.005. My standard deviation is the square root of 0.015 squared over 50. And my mean is 0.580. So the cut-off point, my lower critical region, is 0.575 to 3 significant figures. I also now need the probability that the mean is greater than D1 is 0.005, which would on my calculator mean the probability of getting less than that value is 0.995. So I'm going to put this in my calculator to find my upper bound critical region. So my area is 0.995, everything else is the same. So that is 0.585 centimetres to 3 significant figures. So I haven't actually quite finished. I need to summarise my critical region. So therefore my critical region that would allow me to reject my null hypothesis and say the machine has changed is when the diameter is smaller than 575 or the diameter is greater than 585. If it's less than 575 or greater than 585, then it is part of our critical region and we can reject our null hypothesis. It says the mean diameter of the sample is calculated to be 0.587. Comment on this observation in light of the critical region. Well, I've said that anything greater than 0.585 is within our critical region. 587 is within our critical region. It is larger than 0.585. So therefore, I'm going to reject my null hypothesis and accept my alternate and say the mean diameter has changed from 0.580 centimetres. It's within our critical region, so it must have changed from 0.580. So we reject the null and accept the alternate.